Hello, and this is the presentation about anomalies, breaks, and outlier detection in time series. What I'm going to be discussing is slightly different from the abstract I submitted a few months ago. I actually wanted to react to some of the definitions, some of the new technologies Steven was showing, and so. I assume, actually, it seems that everyone who wanted to be here is here, so I'm going to actually go to, not going to expand too much on this slide, but most of the material here has been already put into the Quantile Regression live coding sessions. Defining anomalies, it can be done in several ways. I should have put probably some graphics here, but we have like point anomalies, contextual anomalies, break points or change points, and structural breaks. Roughly speaking, the point anomalies are any kind of outliers, like say, let me see, I should have some data here. Like say, this here, it's like a point anomaly. We obviously have some kind of groups, and these are more contextual. And in certain situations like here, we have like a change point or break point. So there's too many people and too many algorithms exist for doing this kind of determination of anomalies or whatever anomalies are. People use different definitions. People use different algorithms. It's a very fruitful subject, apparently. If you have like a very strong anomalies finder, and this is something, say, Steven mentioned in the keynote yesterday, you can actually do quite a lot of anomaly detection already with using some simple techniques. I'm going to show that. There are a bunch of anomaly detection packages. This is just two I have found. And this is like, there's some benchmarks. This here, I already showed you the part of the Numenta benchmark, where like 40 time series. And there's similar benchmarks with a competition and for forecasting competition with, say, 100,000 time series. So it's, they're just for forecasting, but of course, we can actually ask ourselves, can we forecast anomalies? This is examples I already showed. As you can see, we have different type of, this is from the benchmark, Numenta benchmark, and we have different type of anomalies. This is a different data set. Do we see anomalies here? We can claim yes. Basically, this is data from the variables and some measurements done at the building of the National Renewable Energy Laboratory. And I'm going to, if I have time, I'm going to discuss some research based on that. In general, this is the flavor here I want to kind of do for this talk. In general with mathematics, but in general with machine learning, data science, we're trying to make enthusiasm to be a good replacement of expertise. And in order to do that, there's certain tooling and methodologies that have to be provided. I'm going to actually mention a couple of things I think it's very fruitful to do when we do this kind of research for anomaly detections. I'm writing a book. Okay, if I do the satire part of the previous talk, I'm also having an upcoming book called How to Be a Data Scientist Imposter. And the importance of the data scientist imposters is tremendous because I want to speed up the next artificial intelligence winter to come faster. So I want to kind of remove as many data scientists as possible, and then produce more interesting research. And how I'm going to be doing this? Actually, yeah, that's interesting, but let me show you how. So basically, this here, it's very similar to the Wolfram Alpha notebook edition. And so this here, it's a series of commands that have been natural language commands that have been interpreted in order to make this evaluate, find these outliers. And here, like again, with some natural language commands, you can see this is the code being generated under the hood with these commands. And then if I copy and paste this code, this is what has basically happened. I can produce this this plot. So how is this similar to what we have seen before? Well, the code generation part with natural commands, we cannot be actually that precise when we are specifying parameters of different algorithms. So this here, it's not an end user command sequence. This is more for data scientists or data scientist imposters. I generate the code, and from the generated code, we do some further manipulations, and we do produce some other stuff. So this here, you can see like it's very similar. I mean, I'm going to explain some of the outliers we're going to detect. So before doing that, I need to return to this slide here, in which I want to say that I do have 2 or 3 or 5 or whatever, but only 3 in this presentation, one-dimensional outliers. And these one-dimensional outliers, I'm going to be using them for doing different related time series finding anomalies and outliers. So you see this is the Hampel, the S plus, and the Quantile identifier. The Hampel one is much more permissive. You can see the outliers detected by Hampel in red. And the other 2 are a little bit more conservative. The S plus one is the most conservative. And so back to this example here. So the thing is that very simply, if I put some regression quantile from my time series, I can reduce the identification. This is in blue. I'm not sure how well you see it. But I can reduce the identification of the time series outliers into this one-dimensional type of one-dimensional problem, and basically pick the outliers which are, say, above or below certain threshold. Actually, what I'm doing here. Here I'm actually using the S plus quartile identifier. Basically, it's picking the outliers in these errors, and so here we can plot them and see how well this maps. Obviously, another approach here, instead of using that outlier identifier, I can actually specify a threshold. Basically, I'm saying anything which is above this line parallel to the axis 50 is an outlier, and again, I'm going to be producing this. All right, so great, but what, I mean, how good is this? I mean, you can always come up with some method like this, and so obviously we need to figure out how to measure success. And this is somewhat the bad news in this field. Nobody has agreed on a consistent metric, and so again, one of the things if you want to do data science or be an imposter, data scientist imposter, you need to figure out the measure of success fairly quickly. You need to measure often, and so this is a very important thing to figure out before going further, especially when we're developing machine learning algorithms. We're not just, say, doing data studies. So here in this presentation, I'm going to use receive operating characteristics and modifications of that and some ad hoc metrics. So another thing, if you want to practice data science successfully, I advise people to acquire software engineering skills. And software engineering skills means software architecture, which is a lifetime quest, and it's kind of hard to teach, not in, say, some book about imposters or whatever. But doing unit tests and figuring out how to do different scaffolding data sets in order to test the parameters, the boundaries of your algorithms. This is extremely important. So this is what's happening here right now. I have these few algorithms here, which basically take a normal time series, and not normal, but some time series, and they produce certain outliers. And I have specified how many outliers I want, and with what factor, and etc. So similarly, I can produce from this time series. I can just pull out some fragments, like below and above, and produce this type of time series. So I'm going to be using this for tests. So this is where we're discussing the testing. So here, this is just my original data I'm kind of showing. And again, I apologize. This should be, I should be doing.
Grab the image and not the box.
Thank you. All right. So so with this, I have done some of this, finding anomalies by residuals, and I'm using the S+ quartile identifier. Earlier, we saw that using with natural language commands. This here, it's just the monadic pipeline. So here I have found some outliers. Then I actually have different parameters with which I can do this, what we see here, right? I mean, I can use a different identifier. I can use relative errors or absolute errors. I can change the thresholds. So I have made this list of parameters here. You can see, like different thresholds, different identifiers, and so forth. And after that, I'm actually trying to figure out here, do they, what is some simple metric based on intersection, which one is, say, the best, or what is producing good results. Instead of using intersections, it's much better to use receive operating characteristics. Here I'm using a package for calculating receive operating characteristic functions. And here I'm comparing the standard true positive rate and false positive rate. Very often, people would actually say, we want to use the positive predictive value. And so this is what this plot is here. And I cannot find a reference, but in a presentation or an article, I have seen some people using weighted version of the recall, the true positive rate, and the positive predictive value. And so actually, this should be live, I think. Yeah, so basically here, obviously, we don't need to use just 1/3 or 1/5 or whatever. I mean, we can see how this, I don't see radical change, although there's some kind of changes. If I increase this argument, this weight, some of these algorithms start to look better or less favorable. So so why I'm doing this? Measuring the success in the previous example here, right? Measuring the success of finding these outliers. I mean, this is the reason. I do actually want to find out, are these algorithms working first? And second, which set of parameters is better? And then if I have certain benchmark with certain type of time series, I actually want to train, say, my models, the parameters to be selected against that benchmark. So here, before talking about the components, we need to talk about structural breaks. So basically, I have this time series. I want to identify these components here, in different colors. And the question is how successfully I can identify the components. Alternatively, you can say that I need to identify these points here. These are the change points or the break points. But, well, I'm going to be identifying the components as a whole, and I'll explain why. In order to do that, I need to first talk to you about structural breaks. Structural breaks were not outliers. Here is an example. You see, actually, there's a line here. It's a blue line. So if I take this one, so structural breaks, the points themselves were not outliers. But if they are a splitting point, which splits the data set in two parts which have very different modeling parameters. In this particular case, I'm using linear regression. You can see the fitted lines very different. So I have this. I have this algorithm here for using structural breaks. Let me see, can I do something else here? So basically, the show test statistic, which is testing for how different the models are, is being systematically applied. Then, using some of the quantile regression algorithms I have, I identify these local peaks. So basically, what's happening here, it's this. From the gray points, and I apologize, there's a blue line here. From the gray points, which are the show test statistic, this blue line is the quantile regression. It's made from quantile regression. And in that blue line, I can, because Mathematica is a symbolic system, I actually can do differentiation. I can find the local extrema, local maxima, and use those local maxima to actually find these fuzzy peaks here, and then use these fuzzy peaks to produce these candidates for structural breaks. Yeah.
I hope this is not inappropriate thing to say.
Yeah.
But this one is an easy problem.
This is what?
This is an easy problem in that anybody who looks at financial time series would say, oh, something was happening and it stopped happening and something new started happening. So you didn't need to really say, was there a structural break? The more challenging problem is when it's not so easy, when it's not so visibly obvious. And is that a relevant question?
You are talking from the perspective of someone observing the time series, scratching their head, pointing a finger. Yes.
Right, yeah.
Also, recognizing cats is an easy problem, but we still do machine learning algorithms for recognizing cats and dogs. So this here, what we are doing is actually to automate this recognition process and run it against multiple series, which are also in some benchmarks and etc. I can expand on this. I'm having a very short time to finish this here. So here you can see with this, basically with the structural breaks, I find very good candidates for the change points. And here I have found this is the outcome of what I got from the components. And now the question is, how good is this? How good is this? Well, instead of using receive operating characteristics, I'm using intersections. And you can see I expect this actually here, if I do some statistics on the fraction of the test data and the components which are found, what exactly, what are the fractions, I do get very good results. Here I opportunistically use Quantile Regression to show a different way of identifying the components in the time series. All right, so I actually, I do have quite a lot of other things to discuss, but using the natural language, I'm going to just skim. This is the detailed, this is the harder part of the talk, the detailed descriptions. I finish with that. One thing or two or three things I don't see people doing is using natural language techniques for representing time series. Here an example about that. You can see this in more details in the live coding sessions. I'm not going to expand on this. One of the reasons though, but I'm going to use the opportunity here to explain something else here. You see, I'm actually seeing the signal as a total thing. I'm not actually predicting something as a stream to be upcoming. And so this is one of the things, this allows me to do this kind of analysis. The other is that Quantile regression is very robust. You see this fitted regression quantiles here. Quantile regression does not get biased easily by outliers. If I did the previous things, the previous algorithms I showed, if I use linear regression or something else, the outliers would have biased the model. But Quantile regression, using quantiles, they are more robust estimator. The other thing is that you see the signal here, it's heteroscedastic. This means that the variance depends on time. If I go back to one of the original slides here, which I skipped, is that I actually, it's here. Using Quantile regression, I can very, very easily find anomalous points, which are anomalous because of the variance. The points which are found here, they're because the variance is much lower than the others, and here the variance is much larger than the others. So this is a fairly unique ability given by Quantile regression. People, for whatever reasons, don't use it as often as they should. So anyway, with using the symbolic representation of the time series, we can do some interesting analysis, like say the mosaic plots. You can look at conditional probabilities. We can apply this here, this prefix tree you see here. It's very similar to what you see when Google completes your phrases or checks your spelling. So dimension reduction, actually, that's a gorgeous example. I'm going to do it. All right, so let me see. So imagine you have a time series like this. And I actually, the way I generated this time series is through this mandalas, or whatever. And imagine that these mandalas, they have been serialized, they have been sent through some channel, and I'm getting this time series. I'm having outliers. And now what we're seeing here is with the dimension reduction, first we have found the individual components, constituents of the time series, and this is just some kind of fancy interpretation. But what else is that we actually can approximate, you see I have picked some kind of image here, and I can approximate it with this dimension reduction. By definition, using dimension reduction and reconstructing the original entities, it's a denoising procedure, so some outliers are going to be removed. A very important perspective is using, from my perspective, it's using operations research and how we use data analysis in general, data science, machine learning to solve operations research problems. You see here, this is the NREL data, the National Environmental Renewable Energy Laboratory. The original signals are in red, the simulated signals are in blue. The thing is that if I combine some of the combined values between the blue signals, they might be illegal. You can see this, like say, with temperature and pressure. I might simulate the pressure and the temperature separately, but this doesn't mean that in conjunction they produce good results. This is exactly what is happening here. I'm illustrating this by using I can learn the distributions, but I can also do this with find anomalies. So basically here, I have found some anomalies in my simulations. And these are points which I'm going to say remove, and then if I remove the points, I can have more faithful simulation of the whole process. So I'm taking some deterministic variables, say temperature, occupancy, trying to predict electricity consumption. I'm simulating each of these deterministic, these regressive variables separately. The combination of these variables, it's not necessarily something that I have seen in the data. So I have made also some other anomaly identifiers. And this, using recommender systems or using this geometric nearest neighbors, which was shown here, they have different performance when find anomalies. They're also faster. This is the last thing I'm going to show, and I don't have time to discuss it. But we have discussed anomalies in single time series. But obviously, we should be interested in anomalies globally is a given time series anomalous by itself? If you look at a big collection of time series. I do have a search engine for time series, and here you can see how this search engine, I have basically drawn some profile, and I have found the most appropriate or the closest time series to it. And similarly, I can find this with using nearest neighbors, figure out which of the signals have the least amount of nearest neighbors. There are references here at the end of the presentations, references throughout. And yeah, thank you for your attention.